Today we are going to learn about optimizing hyperparameters for model performance. We'll delve into techniques like grid search and random search to effectively tune hyperparameters, ensuring enhanced model performance. Welcome to our exploration into the world of hyperparameters. These special parameters are not learned during training but set before the learning process begins. Think of them as the settings on a complex machine that determine how it operates. Adjusting these settings can significantly influence the outcome of your machine learning models. Unlike model parameters, which are learned directly from the data, hyperparameters control the entire training process, impacting the model's performance. Proper tuning of hyperparameters is crucial to harness the full potential of machine learning algorithms. In this video, you'll learn how to master this essential aspect of model optimization. Let's delve into some of the most common hyperparameters you'll encounter across various machine learning models. For neural networks, the learning rate is a crucial hyperparameter that dictates how much to update the model in response to the estimated error each time the model weights are updated. In decision trees, the maximum depth determines how deep the tree can grow, impacting both its complexity and performance. When working with clustering algorithms like k-means, the number of clusters is a hyperparameter that specifies how many groups you want the data divided into. Regularization strength is pivotal for linear models, helping to prevent overfitting by adding a penalty for larger coefficients. Lastly, in training processes, batch size determines how many samples are processed before the model is updated. Understanding these elements is key to tailoring your approach to different machine learning tasks effectively. Grid search is a fundamental hyperparameter tuning technique that involves an exhaustive search through a specified parameter grid. Imagine a grid where each point represents a combination of hyperparameter values. Grid search evaluates each point to find the combination that yields the best model performance. This method is advantageous because it systematically explores the parameter space, ensuring that no potential combination is overlooked. However, it's computationally intensive, especially with large datasets and complex models, as it requires training and evaluating the model multiple times. Despite this, grid search remains a popular choice due to its simplicity and thoroughness. In practice, implementing grid search using scikit-learn is straightforward with the grid search function. This tool automates the process, evaluating different hyperparameter combinations using cross-validation to determine which yields the best performance. Random search provides a compelling alternative to grid search by randomly sampling from the hyperparameter space. Rather than evaluating every possible combination, random search selects random combinations, which can be more efficient, especially when dealing with a large number of hyperparameters. This method often finds a good solution faster than grid search since it doesn't need to evaluate every possibility. However, it carries the risk of missing the optimal solution since not all combinations are tested. Random search works particularly well when only a few hyperparameters significantly affect model performance, and is implemented easily using the randomized search function in scikit-learn. This function helps streamline the process, making random search a practical choice when computational resources or time are limited.
Cross-validation is a statistical method used to estimate the skill of machine learning models. It enhances model evaluation by splitting the dataset into multiple parts, training the model on some parts, and testing it on others. This process reduces the risk of overfitting, providing a more accurate assessment of how the model will perform on unseen data. Several techniques exist, including k-fold cross-validation, where the dataset is divided into k parts, and the model is trained and evaluated k times, each time with a different part as the test set. When integrated with hyperparameter tuning, cross-validation ensures that the model's performance is robust and not a result of random chance. Using cross-validation with grid search or random search helps find hyperparameter combinations that generalize well to new data, making it an indispensable tool in the optimization process.
Let's explore practical examples using scikit-learn, a powerful library for machine learning in Python, to implement hyperparameter tuning. We'll start with grid search using grid search. This function automates the process, requiring you to specify the model, the parameter grid, and the evaluation metric. For random search, randomized search performs similarly but samples random combinations. We'll use example datasets like the Iris dataset or the Boston Housing dataset to demonstrate these techniques in action. After running the searches, the results are stored in the CV_results_ attribute, offering insights into the performance of different hyperparameter combinations. By analyzing these results, you can identify which parameters yield the best performance and apply these findings to enhance your models. Practicing with scikit-learn not only solidifies your understanding but also equips you with the skills to tackle real-world machine learning challenges. Automated hyperparameter tuning tools have emerged as powerful allies in optimizing machine learning models. These tools leverage sophisticated algorithms to streamline the tuning process, saving time and computational resources. Among these, Hyperopt is a popular choice, offering a Bayesian optimization approach for finding optimal hyperparameters. Similarly, Optuna is another efficient tool that automates the search process using an adaptive sampling algorithm. These tools not only automate the exploration of the hyperparameter space but also incorporate advanced features like early stopping, which can halt less promising trials to focus on more promising ones. While each tool has its unique strengths, selecting the right one depends on your specific needs, including the complexity of your model and available resources. By employing these automated tools, you can significantly enhance the efficiency and efficacy of hyperparameter tuning, leading to better model performance. Effective hyperparameter optimization is both an art and a science. Start by defining a broad search space to ensure that you don't miss potential winning combinations. It's important to prioritize hyperparameters that have the most significant impact on model performance. Balancing exploration and exploitation is crucial. While exploring new combinations is important, exploiting known good configurations can also yield high returns. Leveraging domain knowledge can provide valuable insights, allowing you to focus on the most promising hyperparameters. Remember that hyperparameter tuning is an iterative process. It often requires multiple rounds of tuning, analysis, and adjustment. By following these best practices, you can systematically and effectively optimize hyperparameters, enhancing your model's performance and reliability. To bring our learning to life, let's examine a case study where hyperparameter optimization made a significant impact. In this example, a team working on a predictive analytics model for customer churn faced challenges with model accuracy and generalization. They employed grid search to explore the hyperparameter space of their chosen algorithm, initially focusing on parameters like learning rate and tree depth. Despite some improvements, the computational cost was high, prompting them to switch to random search, which provided a better trade-off between exploration and resource usage. The model's performance before tuning was moderate, but after optimization, it showed substantial improvements in accuracy and reduced overfitting. Lessons learned included the importance of patience and the need to continuously adapt strategies based on interim results. As they look to the future, the team plans to incorporate automated tools like Optuna to further streamline their optimization process. This case study highlights the real-world impact of effective hyperparameter tuning and the continuous learning journey it entails. As we conclude our deep dive into hyperparameter optimization, we've explored a variety of techniques and best practices essential for enhancing machine learning models. From the exhaustive grid search to the more efficient random search, and the use of cross-validation to ensure robust evaluation, each method plays a pivotal role. Remember, effective optimization is an ongoing learning process. We encourage you to practice these techniques, experiment with different tools, and continuously refine your approach. By doing so, you'll be well equipped to unlock the full potential of your models, driving better performance and impactful results. Thank you for joining us on this journey, and we look forward to seeing how you apply these insights to your own machine learning endeavors.